In Chapter 3, we talked about reactions taking place in general, and we looked at general properties of reactions and how reactions occur and how you predict reactions and all those things. In Chapter 4, we're going to start focusing on one essential ingredient that basically is required for a reaction to happen. In Chapter 3, we basically made assumptions that when you put some things together, we could predict the products. But what we really didn't talk about was the fact that in order for reactions to occur, the ions and particles need to be free to move. And without being free to move, they really don't interact a whole lot. For that reason, water ends up being very essential in most chemical reactions. So what we focus on in Chapter 4 are aqueous solutions. Aqueous, the word aqueous comes from the Latin aqua, which means water. So an aqueous solution is a solution in which something is dissolved in water. And there are two parts to every solution. The solute is the substance that is being dissolved. The solvent is the substance that is doing the dissolving. Now, one common misconception that you need to clarify is that solutions, although often we think of them as being a liquid, in reality, solutions exist in all three phases of matter: solid, liquid, and gas. To give you examples of each. In the solid phase, we have gold jewelry. When you buy gold jewelry, pure gold is 24 karat gold. Now, you might buy jewelry that's 24 karat gold plated, but it's not 24 karat gold the whole way through. The reason why we don't buy 24 karat gold jewelry is because 24 karat gold jewelry is so soft and brittle that you can dig your fingernail into it and dig a gouge out of it. So it's very soft. Most people wouldn't want jewelry that soft. Rings, earrings, necklaces, they would break very easily. So what we do is we make a solution of gold with some other more durable metals: stainless steel, tin, copper, and cheaper jewelry, silver in some cases. But gold jewelry is a solution in which gold is dissolved into some other metal that is more durable. In the gas phase, the air we breathe is a perfect example of a solution. The air we breathe is a solution of three main gases: oxygen, nitrogen, and carbon dioxide. About 78% of the air we breathe is nitrogen. About 18% is oxygen, and about 1 to 2% is carbon dioxide and some other trace gases. If the air we breathe was not a solution, was not mixed together evenly or homogeneously, we would not be able to survive. We would have to find oxygen pockets to survive. But we don't, because the air we breathe is mixed together very evenly. Obviously, in the solution phase, or the liquid phase, which is the one we're all familiar with, Kool-Aid would be an example. If you've ever made Kool-Aid, you take the Kool-Aid pack, you take the sugar, the water, you mix it together, and you make a solution that way. So in chemistry, we talk often about things being dissolved in water. Now, we're going to talk about that word dissolve throughout here, and whether something is considered to be soluble. In order for something to be considered soluble or slightly soluble, there's a set of rules, and what textbook you go by and what source you look at really differs. In general, what we say is, in order to be considered soluble, if at least 0.1 mole of a substance will dissolve in a liter of solution, we generally say it's soluble. Now, the things that we consider to be soluble are things that will dissolve in water to some extent, or to a fair extent. Things that we consider to be insoluble in water are things that do not dissolve for the most part. However, things that are insoluble, it is not meant that they are completely insoluble. All substances are soluble to some extent. They will dissolve to some extent in water. Water is what we call the universal solvent. It is a polar substance, and therefore it makes it great for breaking apart ionic compounds. So what we're going to do is we're going to use the solubility rules to define which compounds will be soluble and which compounds will not be soluble. And in your textbook there on page 125, they're in table 4.2. And I think I've provided them on later sections of notes as we get to them. Now, when things dissolve in water, ionic compounds in particular, molecular compounds, clarify those two terms again as a review. Ionic compounds, as you remember, are a metal and a nonmetal, or a metal and a polyatomic ion. Molecular compounds are compounds that are two or more nonmetals joined together. And then acids, we know, are hydrogens and something else. When you put those substances in water, how they behave in water is completely different. Ionic compounds generally form what we call electrolytes. Now, an electrolyte is a substance that, when dissolved in water, will conduct electricity. It generates ions, or it breaks down into its component ions in solution. There are two types of electrolytes we deal with: strong and weak electrolytes. The difference between them basically is just a matter of to what extent will they dissociate. Now, the word dissociate and dissolve do not mean the same thing. Dissociate is referring to how much do they break apart into ions. Dissolve means they break down to small particles that are not visible to the naked eye. So things can dissolve and not dissociate at the same time. However, if they do dissociate, they do dissolve. Strong electrolytes are substances that when you put them in water will completely dissociate into its ions. For example, sodium chloride. If I put sodium chloride into water, it will break completely apart into sodium +1 ions and chloride -1 ions. It will no longer exist in solution as NaCl. It will only exist as sodium ions and chloride ions. Strong electrolytes will completely dissociate in water. Now, the things that are classified as strong electrolytes are ionic compounds, which you know how to identify as a metal and a nonmetal, strong acids and strong bases. At this point, you do not know how to identify those, so for the time being, just know that strong acids and strong bases are considered to be strong electrolytes as well. We'll talk more about those in the upcoming sections. Weak electrolytes undergo what we call partial dissociation or partial ionization. Those two words are sort of synonymous with one another, which means they'll exist as both molecules and ions in solution, and we say they undergo equilibrium or are reversible reactions. For example, hydrofluoric acid is a weak electrolyte. It's an acid, but it's a weak acid. It's a weak electrolyte. The way we represent its dissociation is with a double arrow. This symbol represents equilibrium. So when you see a double arrow like that, what that means is some things are breaking apart, going to products. So we have some H+ ions being formed and some F- ions being formed. But at the same time, these things recombine to come back this way to form some of that original reactant. So at any given time in solution, we have some of this, and some of that in solution. So weak electrolytes will partially dissociate. At any given time, you'll have some molecules of the original substance and some ions. Again, strong electrolytes completely dissociate, so in water you only have ions present. Now the third type of electrolyte, or the second type actually, is called a non-electrolyte. And as the name says, a non-electrolyte will not conduct electricity in water. Right? So they do not conduct electricity in water. Molecular compounds are things that are classified as a non-electrolyte. Sugar, for example. We all know that sugar in water will dissolve in water. It will not dissociate. So when I put sugar in water, C12H22O11, it, in solution, may dissolve down into smaller particles that you can't see to the naked eye, to small molecules, but in solution it will not dissociate. They will still stay together as C12H22O11. They do not break apart. Molecular compounds are always non-electrolytes. So as a recap of the three types of electrolytes, electrolytes means they'll conduct electricity, non-electrolytes won't. Now within electrolytes there are two types, strong, which means they totally dissociate. They are ionic compounds, strong acids and strong bases, which we will touch base on here in the next couple of sections. Weak electrolytes are things that will partially dissociate or undergo equilibrium, and they are weak acids and weak bases, again, which you should not be able to identify at this point, but we will in a few sections. And then the final one are non-electrolytes, which are molecular compounds, two or more non-metals joined together. Now, what causes water to break apart things, ionic compounds, is that it is a polar solvent. When water molecules exist, they look like this. We have hydrogen molecules out here. We have an oxygen molecule here. The oxygen molecule tends to take on a negative end, and a positive end is where the hydrogens are. So we have what's called a polar solvent. Polar meaning it has poles like the poles of a battery, a negative and positive end. Ionic substances also have negative and positive particles, as we learned earlier. So the negative end of oxygen will start tugging at the metal ions, and the positive end of the hydrogen will start tugging at the negative ions. So water will pull apart these things in a process called hydration. And you'll see more about that in a animation exercise coming up.